Equalization, equally important. Equalization is often abbreviated as EQ. This typically consists of several filters of varying types under one interface. Usually there's knobs or potentiometers or sliders to control the parameters of these filters. So there are maybe two kind of filters you often find on equalizers. There are peaking filters. These are similar to the bandpass filters, except they affect only a narrow band of frequencies on a peaking filter. Shelving filters are much wider. Probably your home consumer stereo system, which has a treble and a bass, that's a shelving filter. What it does, it has a wide range of area that it will affect, and it usually just affects above or attenuates or amplifies above a certain cutoff frequency, and it's a very simple kind of filter design. So your car stereo will usually have shelving filters as such. So when we look at the various kind of equalizers on board software programs, they will usually be in one of two different kind of formats, either what's called a graphic equalizer or a parametric equalizer. The graphic equalizer will have multiple slide faders on it, and usually each slide fader is a predetermined slice of the spectrum that slide fader will either amplify or attenuate the energy at that range. So if you have say for example a 10 band or 20 band graphic equalizer, you can then go through and look for different kind of slices of the spectrum to alter the equalization of that signal. The parametric equalizer doesn't have as many bands, but it does in some ways give you more precise control. A parametric will often have between 3 to 8 different bands on it, or filters. And usually these are going to be low pass or high pass filters, or even shelving filters. And when we divide that spectrum into these 8 different bands, each one will also have ability to control the center frequency for that band. So whereas the graphic is a fixed center frequency that each of those slide faders controls, here we can have 8 bands, but we can move the center frequency to wherever we need to. And then we can also often have a resonance control which will affect the width of that control. So usually a parametric, you will have between 3 and 8 different bands, but each one will have 3 controls. You will be able to set the amplification attenuation level, you'll be able to set the center frequency, and then you'll be able to set the resonance, or how wide of the frequencies, the band you want that to affect. So in some ways, a lot of sound engineers and people prefer the parametric because it gives you more specific control. And many of the software programs will be looking at, when you pull up a equalizer, often it's going to be a parametric design more than the graphic design. So time-based effects, what are the time-based effects that we're looking? So a time-based effect, in essence, is a memory space in the software that will store the incoming signal for some period of time and then combine it with the original dry signal. That's basically what it is. It's a buffer of sound that the sound comes in, gets stored, and then get re-articulated and combined with the original sound source. So the most simple would be a delay. So a stereo delay often is what we have on various effects processors. So what will happen is the sound will come in, and then the sound will get re-articulated with a certain time delay on that. And that delay can be done both with the same spatialization, or it can be panned left or right. So often your stereo delay, the sound will be coming back and re-articulated, but it would be changing channels. So you get this sensation that the sound is kind of moving around the room in your stereo delay. So echo is a particular kind of delay, and sometimes when you pull up an echo effect, the delay will be more than 50 milliseconds. So any delay that happens longer than 50 milliseconds after the original sound articulation is referred to as an echo. So usually, acoustically, you can hear an echo if you can find a room where there are parallel walls, and you make a sound, like you clap in that sound, and the sound will, because there's nothing to absorb it, you can hear the sound bouncing back and forth with no deterioration of sound, and that produces the echo effect of a kind of a more than 50 millisecond delay. If you have a large enough room, then the sound will have a longer echo to it. Generally, in reverb situations, we try to avoid echo. So acoustical engineers, when they're building concert halls, they always try to avoid parallel walls for that reason, because you don't want any kind of what's called a flutter echo to be occurring in an acoustical environment. So there's a very intentional way of getting rid of that. But electronically, we can always put an echo in there if we like that effect. What you'll also find in other time-based effect is something called a chorus. A chorus here, again, is another type of delay, but it is usually within the 10 to the 50 millisecond range, and people will use a chorus to what is called fatten the sound or enrichen the sound. And it's not just, for example, what is the difference between a solo articulation, say a solo singer singing a series of notes, and a chorus singing the same thing? The chorus, you will find multiple performers who aren't exactly lined up, exactly on the right pitch, and exactly at the right time of articulation. So what makes the chorus effect is where you have multiple articulations slightly apart in time, but also the pitch is often slightly off, but not so much that it sounds out of tune. What that does is create a single sound becomes, quote, fatter or richer when we hear that. So the chorus has to have both a delay in it of 10 to 50 milliseconds, but it also has to have some kind of LFO, low frequency oscillator, that can modulate the pitch. So you can either get a slight delay and sometimes a frequency change so we can slightly get it out of tune. So a chorus has multiple things going on in it, but it produces a richer, fatter sound. And perhaps chorus is one of the more common time-based effects. Flanging is another effect. This is a delay of less than 10 milliseconds. So what happens is that you modulate the delay with an LFO, but it results in a sort of a shifting of the peaks and notches as the spacing between the two phase together kind of widen and narrows. So a flanging usually is controlled by an LFO of time where you can hear that millisecond moving in and out with an LFO, and you get this very specific kind of effect that we call the flanged effect that results in that. But here again, it's another type of delay with less than 10 milliseconds, but controlled by an LFO similar to what a chorus has. Phasing is somewhat similar to flange, maybe in its effect, but it's done in a very different way. It produces a sort of shifting of the notches in the spectrum, but uses what is called all-pass filters. An APF, an all-pass filter, passes all the frequencies through, but changes the phases of the partials. So the phasing would mean, if you remember in design you have a compression and a rarefaction. If we change the phase of a waveform, we would then start with the rarefaction before the compression. So that way, by having different signals put against each other where the phasing is changing, that you find this timbral shift that goes on in the sound. So phasing has a similar kind of impact to flanging, but it's done in a very different way with this all-pass filter effect. And then the final most common base time impact effect, as I mentioned, is reverb. Reverb is best used as a send effect rather than an insert effect, so it becomes after other processing is done. A reverb is a particular kind of effect that has usually three parts to it. The reverb will have your direct sound that we want to hear. Because now remember, in reverb, we're trying to model the acoustical room phenomenon. This is not some electronically processed sound. This is usually trying to simulate the feeling of a particular space, a physical space. So in physical space, we always hear the direct sound first. Then usually there's going to be what are called early echoes. The early echoes are the early reflected sounds where we have sound bouncing off the walls, the ceiling I mentioned, and usually those, because of the material of the walls, the high frequency partial content will be absorbed in those reflections. So not only in the early reflections do we need to have a very slight delay of sound coming to our ears, but it needs to be a different timbre to where the high frequencies are reduced in that. And then usually in larger spaces, the third area of reverb will be what we call the dense echoes or the dense reflected sound. So usually the first reflected sounds that come to us are the ones that we can hear still clearly, but we have some reduction of the high frequencies. But what the dense echoes are is in some spaces the sound will just keep bouncing around for some time. And we're still hearing that in the sound. As we get those dense echoes, they really are much lower, because a lot of each time they hit a wall, it reduces more of the high partial content, and the sound is deteriorating over time as it does that. So what you get is more of a darker, kind of rumblier sound to the dense echoes. So when you're creating a reverb, usually you're going to have those three different kind of parameters to make a very flexible reverb. We can also find two different kind of plugins that you'll find on reverbs. The most standard, perhaps, is the artificial reverb, which we're just describing, where we would use filters and delays to mimic what we were just talking about. So what we would need to have the reverb we were just talking about was to have some delay for the reflected sounds, and then to have some kind of filter that would take out those high frequencies as the longer delay went on. So obviously, an artificial reverb would be just a combination of filters and delays. There's another more interesting way that has emerged recently with some programs, such as some of the commercial programs like the Apple Logic program and Pro Tools and so forth, have what are called convolution reverbs. And what these programs do is they take what are called, they utilize an impulse response recording. So what they will do, they will go into actual spaces and they will record a very short sound into that space. That short span will be the impulse. The impulse will then create a response in that space. And they can measure exactly what happens to that impulse in that space. And then that sharp sound, they can model that sound and take the same parameters as a kind of a mathematical convolution. And there's here again, an algorithm. An algorithm will then be created to model that particular space. So when you see in some of these commercial programs which have these convolution reverbs, you'll have a listing of various kinds of spaces. You could have a very live cathedral, such as Notre Dame in Paris, or a space in New York, or very specific spaces. A lot of times they will have models for those, which are these mathematical analysis of the impulse in those spaces, and then those are applied to whatever sound source you come in. So in some ways those are the most interesting, because you could have multiple spaces of the Taj Mahal in India, or anybody that has recorded those would create these models, and you can very specifically make it sound like a sound would be in that particular space. So it's not an artificial manufacturing, it's actual kind of a sampling of that, and that's the convolution reverb. So other kind of digital audio effects that you may use, and you will find many in our plugins, would be tremolos. Remember, tremolo is the alternation of a simple amplitude modulation or a sort of a human rate amplitude modulation. There are various kinds of distortions that we will use, which are wave shaping functions, often nonlinear, where we can sort of add distortion we're trying to often avoid in sound design, but sometimes by distorting the signal through wave shaping, we want that quality. You will often be using what's called time stretching and pitch changing. These are very common effects that we'll be talking about once we go to a couple of programs. We'll demonstrate how they work. Sample granulation is another important. If you do have a granular synthesis system, having the sound broken up into little slices of sound and then re-granularizing it is a very common way of putting sound into buffers that we can then process, which is a very interesting ways. And then spatialization, we've mentioned, is an important part of what we do in sound design, so that we place sound in a certain distance from the space, either physically away or moving on left or right, panning, or if we have multiple channels of output, then we can place the sound in, for example, in 5.1, what is a more common media format, or 7.1, where you have 7 channels of speakers around you plus a subwoofer. Or if you go to a modern cinema or theater, you may have 24 channels, 24.2. You have 2 subwoofers and 24 channels around you. So the sound has a location which is very important to how we experience sound. So many effects processors will have very sophisticated spatialization built into them. And then sound morphing is another part, which is really part of a field which is called analysis resynthesis. In analysis resynthesis, you take the sound coming in, you break it down into all of its partial content, and then you resynthesize it by assigning a sine wave to each of those partials. But then once you have got it resynthesized, you have control over the sound, and you can take each of those partials and delay them separately or manipulate them separately. And so with sound morphing, you can get some very interesting kind of relationships. It's a lot more computation to do sound morphing. And so some of the more sophisticated systems we'll be talking about and not doing in this class, but I'll introduce you to, such as Kima is one of the sounds that I use that has a really powerful, robust sound morphing algorithm built into it. So you can take the parameters, say, of a violin and take another analysis of a cat and slowly start to map the parameters of the partials of the violin to the cat, so that the violin is playing but slowly starts to sound like a cat, for example, or an animal sound. So sound morphing is maybe the most robust set of sound design principles, because you can do anything, because once you've got it analyzed and then resynthesized with all those sine waves assigned to each partial, then you have ultimate control over what happens to that sound, and you can turn it into any other sound. So that's the other sound effects. So next we're going to take a look at a program called Soundation Studio, which is an online program. So you can use this with any computer because you'll be doing recording with sound and manipulation of sound, but it'll be done all on another server. So we don't have to deal with which software downloaded to our own computer, because we're doing it all on the web as such. So we will go over and take a look at Soundation Studio and explain and listen to all the different kinds of digital audio effects we just explained.
The preceding program is copyrighted by Emory University.